Booth algorithm. This algorithm works both for a positive and negative numbers. It is much efficient because it reduces the number of additions. It just use shifted values, sequential circuit multiplier. So both negative numbers can also be multiplied through this algorithm. So to understand more about this algorithm, let us consider an example. If the multiplier bit contains 4 number of continuous values of ones. So how to calculate the multiplication for this? So we need to add multiplicand 4 times in a shifted position. So this is not much efficient. We need to add it for 4 times. But instead of adding the multiplicand for 4 times to the partial product, so there is another possibility. The binary equivalent of the decimal equivalent of this number is 30. So 30 can be written as in terms of 2's power 2 power 5 minus 2 power 1. So we can write this as 32 minus 2. We'll get the 30. So instead of multiplying the multiplicand with all ones for 4 times, we can multiply it with 2 and multiply it with 2 power 5 only once and subtract the value. So some x into 32 minus x into 2 will get x into 30. So this concept, so instead of adding the multiplicand for 4 times, so we'll do this. So we add multiplicand. So in first 32 value, we'll add multiplicand only for once. In the second also we add multiplicand for only once, and we mostly use, so in the first one we could add 4 approximately shifted versions of a multiplicand. We'll just shift 4 to 5 and then add the multiplicand only once. So instead of adding 4 times, we can add only once or minus only once. So this concept, based on this concept they implemented a Booth algorithm. So at position 0 we have to subtract the multiplicand. At position 5 we have to add the multiplicand. So this is the concept. So for this multiplier, we'll get the Booth recording as 0 at first position and minus 1 at second position. The first starting one is from 0 to 1. When we move from 0 to 1, we have to complement the bit. Minus 1 is written. And for the same bit, so we do nothing in the 3 remaining. After the last one, we'll use from 1 to 0, we'll just add plus 1. We'll just add multiplicand. At second position, we subtract the multiplicand. At sixth position, we add the multiplicand. So this is called Booth recording of a multiplier. So instead of adding for 4 times, we'll just subtract once and add once in if we have continuous ones. So according to the Booth multiplication, so if we have values at bit position I minus 1 and I, if we have 0 and 0, series will be 0 and into multiplicand. If we move from 1 to 0, value is plus 1, so we'll add the multiplicand. If we move from 0 to 1, we have to subtract the multiplicand, minus 1 into m. If it is 1 and 1, we have to do nothing. We just shift the values. So when we move from 0 to 1, it will be negation. When we move from 1 to 0, it will be addition. Subtraction, addition. If you will take some more example, if the multiplier bit is this, so initially we are at 0. So what is to be placed here? So for first we will keep 0, and for the second we have moved from 0 to 0. So same positions, do nothing, 0. We are moving from 0 to 1. So we have to use multiplier a bit as minus 1. From 1 and 1, for 1 and 1 0. From 1 to 0 we have to use plus 1. From 0 to 1 minus 1, 1 to 0 plus 1, 0 to 1 minus 1, 1 to 1 0, 1 to 1 0, 1 to 0 plus 1, 0 to 0 0, 0 to 1 it is minus 1. So like this we generate both recording of a multiplier. So let us see how whether it works or not. Suppose we have the same example. So we have one product here and one product. The multiplier bit has 4 ones. So we are calculating the multiplication of this through the sequential circuit multiplier, normal long handwritten multiplication. So we'll get the final product like this. If I use minus 1 instead of using plus 1 4 times, if we use both recording, so we'll get it as 0 minus 1 0 0 0 plus 1. So for a 0 we'll write all zeros. For minus 1 we write 2's complement of multiplicand. 2's complement multiplicand is 1 1 0 0 1 and all the ones. For a 0 we'll just use 0 0 0 for 3 loops, and we have plus 1. For a plus 1 we'll simply add multiplicand 1 0 1 0 0 1 and remaining all are zeros. So we'll get partial product like this. So in both the cases the output is same. So what happened, we just used shifted position for 3 times. We subtracted ones and added ones. So addition is also simplified for our both recording. But whereas for the normal multiplication, so addition is also became very tough. So we sometimes need to add 4 bits or 5 bits. But here as we have less number of ones, we can calculate the both multiplication algorithm easily. So these are the circuits or registers required for calculating the both multiplication algorithm. So here we have a BR register. BR register contains multiplicand and AC register which is initially 0. This AC and QR act as a shift registers. The final product will be in both, and QR contains multiplier. Add the multiplicand or we add 2's complement of multiplicand to the AC register. That is why we have a circuit complementer or parallel adder circuit, and we have a sequence counter to calculate how many number of times we repeat the loop, and Qn is the least significant bit of multiplier, and Qn plus 1 is the shifted value of least significant bit. So here is the algorithm. We start initially, we use all zeros to AC, and Qn plus 1 is 0, and AC represents number of bits of a multiplier. BR contains multiplicand, QR contains multiplier. So our multiplication algorithm starts by checking the value of Qn and Qn plus 1. If it is 0 and 1, so if we are moving from 0 to 1, we'll just add the multiplicand to partial product AC. If it is 1 and 0, so we are moving from 1 to 0, then we have to use 2's complement. If it is 0 0 or 1 1, we'll just do nothing, we'll just shift the AC and BR. So for after every shifting, we decrement the AC step counter, sequence counter to -1, and then we'll check the condition for the sequence counter. If it is not 0, we have to repeat the loop. If it is 0, we have to end. Let us take an example. Again I'm taking the same example, -13 into 11. So they will mention how many number of bits to be taken in the question. If not, you can take how many number of bits you want. So 13 can be written as 1101. So for a sign bit I used 0. So minus 13 can be calculated by ones complementing the 13 and adding 1. So we will get the minus 13 value here. So which is a multiplicand. So I have to store this value in BR. And 11 equivalent is 1011. I used sign bit as 0, which is a multiplier in Q. Initially BR is 10011 and AC is all 0. Q contains multiplier 01011 and Q n minus 1 is 0. So sometimes I required complemented value of multiplicand, so that is why I calculated BR plus 1. So I wrote here. Next algorithm. So our algorithm starts. Initially A is 0, Q is 01001, Q n minus 1 is 0, and number of bits of a register 1 2 3 4 5. So check the condition. What is Qn and Qn plus 1? Last bit of Q and Qn plus 1. 1 and 0. What I have to do for 1 and 0? For 1 0 I have to add AC with BR plus 1. Means I have to subtract the multiplicand with AC. So AC plus B, A value is this one, BR plus 1 is this. So I added 0110 to the AC value. So what I get? 0 plus 1 1, 0 plus 0 0, 0 plus 1 0, 0 plus 1 1, 0 plus 0 0, and I placed next I have to, after adding I have to arithmetic shift right of AC and BR. Arithmetic shift right of A and BR. So I copied this value here and I used shifting operation. Shift 0 to the next position, 1 to next, 1 to next, 0 to next, 1 to the Q, 0 to next, 1 to next, 0 to next, 1 to next, and Qnth position will be moved to Qn plus 1. After shifting, I have to decrement the SC. Is SC 0? No, I have to repeat the loop. Next again check. If SC is not 0, I have again need to check Qn and Qn plus 1. So what is Qn value? 1. Qn plus 1 value is 1. For 1 and 1, I have to just arithmetic shift right of A and Q. So for in arithmetic shift right, the sign bit will be just copied as earlier. So here the value will be same as a sign bit that is already present. So that is why I copied the same thing and I moved the each and every bit towards the right side. 0 to next, 0 to next. So this same value is copied for 2 bits. 0 1 1 0 0 0. I shifted every bit of A and Q towards the right, and after shifting I have to decrement the SC. SC is now 3. So now check the condition. Qn is 0, Qn plus 1 is 1. For 0 and 1, for 0 and 1 what I have to do? I have to add the multiplicand to the partial product. So I am copying the same here and I am adding the BR value. BR value is 10011. So 10011, 1 plus 1, 1 0 here, 1 here, 1 plus 1 plus 1, 1 1, 1 plus 0 plus 0 is 1, 0 plus 0 is 1, 0 plus 1 is 1. So again I got the product. I copied the remaining to this place. Now I have to shift right A and Q. So sign bit is copied same and I shifted every bit towards the right and decrement. After arithmetic shift I have to decrement the SC. Now SC is 2. Now check the condition. Qn and Qn plus 1. 1 and 0. For 1 and 0 I have to add Br plus 1. I copied this value. A is 11011. Br plus 1 is 0 1101. 1 plus 1 1 0. 1 and 1 0 1. 1 and 1 0 1. 1 1 1 1. 1 here 1 here. And 1 plus 1 0 here, carry here. So we can neglect the carry. Now arithmetic right shift of A and Q. 0 sign value will be the same as before and shift all the bits towards the right, one position right. Next, after arithmetic right shift, you have to decrement the step count. 2 will become 1. So which is not greater than 0, I again need to repeat the loop. So what is the last bit? 0 and 1. For 0 and 1 I have to add A with BR. A is 0 0 1 0 0. I just copy it to the next line. And BR value is 1 0 0 1 1. 1 0 0 1 1. And add 1 1 1 0 1. Again arithmetic right shift of A and Q. 1 1 1 1 1. I shifted each bit of A and Q towards one bit towards right and decrement the value SC 0. So if when SC is 0, we need to stop the procedure. My final result will be in A and Q. 1 1 0 1 1 1 double triple 0 1. So this is my answer. So because it is 1, the sign bit is 1 means it is in a complemented format. So to check whether it is this magnitude is 143 or not, I am calculating that complement of this. So 2's complement value is 0 0 1 triple 0 double 1 double 1. So it's equivalent to 2 plus 1 plus 2 plus 4 plus 8 plus 128, which is 143. So the value of this answer is minus 143. So our answer is correct. Thank you.